Data structures, a foundational tool in software development, are used for organizing memory. Today we will explore them.
Welcome to Kopek Explains Software, the podcast where we make computing intelligible.
This week, Dave, we're talking all about data structures. Let's start with, what is a data structure?
So I'm going to use a couple definitions from some of the most famous algorithms and data structure textbooks today. So I'm going to start with one from Introduction to Algorithms. It says a data structure is a way to store and organize data in order to facilitate access and modifications. Wow, that is such a general definition. So many things can fall into that definition. If you just think about a file, well, a file is a way of organizing data, and it's a way of accessing it and being able to modify it. So by that definition, a file is a data structure. A string, which is a sequence of characters, and we talked about previously in several previous episodes, is a data structure by that definition because it's a way of putting characters together and getting access to any of those characters in an organized way in a particular order. Even a number, because we know back from our episode, what is a byte? Every number is actually a set of bits. So you could say a number that's stored in the computer is a way of organizing those bits. So it's such a general definition that it's not actually that useful. All we know is that it's a way of putting data in some place and then being able to retrieve it and change it. That's basically what that definition says. So I think what's best today is we'll actually use some illustrations. We'll talk about two specific data structures, types of data structures, and we'll talk about why they're useful. But what I'd say generally to make that definition a little bit more concrete is that when we talk about data structures in computer science or software development, we're typically talking about collections of data. So we're not talking about a single number. We're not talking about a single string. We're talking about how can we put multiple numbers together in an organized fashion for efficient retrieval of specific ones at a specific time.
Why do data structures matter? Why are these collections so useful?
We talked about in our episode, what is a byte, how a byte can be used to represent a number, and ultimately a number can be used to represent a character, or a number can be used to represent a pixel on the screen, or several numbers put together can be used to organize text or used to organize a picture. But what if I want to have multiple different numbers or multiple different strings of text, and I want to have them all in one place? If we think about our previous episode on what a programming language is, in a programming language, I have a concept called variables. And we often have things called primitives in programming languages, and those are really very basic types. They might be something like an integer, so a whole number in other words. And I might have a variable that represents a single whole number. Or I might have a variable that represents a single string. Maybe it's the string hello, right? The word hello is the thing that the string represents. That's useful. But what happens when I have, let's say, all the names of all the people in some class? Now I don't just have one piece of text, like the word hello, or even one name, like the name David Kopek, but I might have an entire class of names. How do I put all of those different names together in one place? That's really the key of why data structures are useful. When we have collections of information, multiple different pieces of data, and I want to put them together in one place so that I don't have, let's say, 24 different variables for 24 different people in a class, because that would just be very hard to keep track of. And I want to just have one variable that represents a single data structure that contains all of those 24 names in one place. And that is a flexible enough data structure that it could work if I had 30 people in the class, or I had 15 people in the class. That's where we start to see the power. So data structures are useful when we have more than just the most basic kinds of information. When we have more than just one of something, then we start to want to have data structures for organizing that collection of data in a way that's easy to retrieve, easy to organize in a specific way, and efficient in terms of its usage of memory.
Let's look at some specific examples to really explore these. What would be a good one to start with?
Yeah, so today we're just going to talk about two different examples. There are so many different kinds of data structures, And they're usually used for very different kinds of applications. They have trade-offs between one another. One will be very efficient, let's say, for retrieving a particular kind of data, and another one will be efficient for organizing data in a particular order. So we use different data structures for different applications, but there are some really fundamental ones that basically every application uses, or at least every programming language has built into it. And we're going to talk about two of those today. We're going to talk about arrays and linked lists. And these are really very, very fundamental data structures that everyone who studies CS or software development gets very familiar with. And there's some really clear trade-offs between arrays and linked lists. So they're going to serve as great examples because we'll see why one might be better for some things and another one might be better for other things. And I'm going to try to keep the discussion high level enough that even those of you who aren't programmers will be able to follow along with the basic ideas that we're talking about.
So we're going to talk about an array first. What is an array?
An array is just a way of taking a piece of memory and saying, I want to pre-allocate it for several of the same type of data. For example, we talked earlier about the names in a classroom, right? So I might have an array of strings, and strings, as we talked about in previous episodes, are used for organizing collections of characters. So let's say I have all those names and I want to put them all in one place. If I just had a single string, it would just hold David Kopek. But maybe now I want to have two strings. So I want to have one string that holds David Kopek and another one that holds Rebecca Kopek. But if I just put them in a single variable, it's going to be confusing. Where does the first name end? Where does the second name begin? If they're all in one string, that's not that useful. What I want to have is I want to have some section of memory where I have little spaces pre-made. And I can put in one of the spaces David Kopek, and I can put in another space Rebecca Kopek. That's what an array is all about. It's about pre-allocating a subsection of memory for the same type of data that's organized in a linear order. So we're having all of them next to each other. And each of those spaces that I've made for those names in an array all get a number. We call that number the index. And it tells us where in the array we're at, which space are we at. And all of the spaces are right next to each other. And usually in most programming languages, we start counting the array at 0, actually. So the first space is actually the 0th space. The first item is in the 0th space. So if I just had those two names and I had an array that just had two slots, then I might say David Kopek is in slot 0, index 0. Rebecca Kopek is in slot 1, index 1. And so now I have a space for two different names. Now, that might not be what I really need. Maybe I need space for 50 names. And so I can allocate an array for 50 spaces, and then for the entire lifetime of that array, I have 50 slots that I can put that type of data in. And usually it's one type of data that an array is allocated for. So it might be allocated 4 strings, or 4 integers, or 4 floating point numbers, which are numbers with decimal points. And then every one of those slots can hold one of that type of data. So array slot 0 can hold David Kopek, array slot 1 can hold Rebecca Kopek, and the other 48 slots, if it was a 50-slot array of strings, could hold 48 other strings. And then when I wanted to quickly access them, I could just go right to the index of a particular space. So for example, I want to quickly know what name is at slot 25. The cool thing about arrays is they have what's called random access. And it's kind of a weird name because random, you might think, that sounds like mixed up all over the place. No, it actually means that we can instantly get to any of those slots. So because we know how the memory is laid out and we know how big each of the items are in memory, the microprocessor can almost instantly, access any of the slots in the array. And so we can go right away to slot 25. We don't have to first go through slots 0 through 24 to get to slot 25. And that idea that we can very quickly get to any of the slots is one of the things that makes arrays so powerful. We can very quickly get to any slot if we just know the index of the slot that we're interested in. So arrays are ways of taking sections of memory, contiguous memory, and the word contiguous means together, next to each other, and pre-allocating it into slots for some particular type of data, and then having indexes that we can quickly get to any of those slots.
An analogy I've heard you use for arrays would be a pillbox. Is that right?
Yeah, it's a great analogy because it really is very similar to a real-life array. What's a pillbox? Oftentimes people who take medication need a little reminder of when they take their medication. And so a pillbox is usually this thing with 7 different slots, one for each day of the week, and each of those slots are labeled, right? They might be labeled Monday, Tuesday, Wednesday, etc., all the way up to Sunday. And each of those slots can only hold pills, right? I can't put donuts inside the slots. They're made for one particular type of thing. So you could think about a pillbox as an array of pills. And each of those individual slots, because they're labeled, you can instantly get to. I don't have to go through and count the first 4 slots to figure out where Friday is. I can right away go to Friday because it has that label, that F on the cover says, hey, this is where the Friday pill is. You don't have to go figure out where the Friday pill is. That's like an index in an array. That's like when I wanted to find out where Rebecca Kopek was in the array of strings, I could instantly go to slot number 1. Because I know that Rebecca Kopek is at index 1. Well, I know the pill I need for Friday is in slot F, so I can instantly go to the F slot. So a pillbox is very similar to an array in real life. And it also has one of the big limitations of arrays, which we haven't talked about yet. And that's that you can't make the pillbox any bigger or any smaller after you've made it.
So you have to know as you're building it, how the total size you're going to need.
Right, you have to know how many days of the week are there? How many pill slots do I need?
How many students are there in this class?
Right. And so when you have that original pillbox, you can't actually go, unless you're like a plastic welder, and go add another slot to it. And unless you want to really get messy and use some like interesting cutting device, you can't really break up the pillbox either. The same thing is true in most programming languages with arrays. You can't easily go and change the size of the array after you've already allocated the memory for it. It's some contiguous set of memory that you've taken aside. You've decided how many slots there are, and you've decided how big each of those slots are. And once you've done that, you're stuck with it. You can't actually go add another slot to that existing array. You can't remove a slot from that existing array. That might sound to you like it's very inflexible, and actually it is. That's one of the limitations of this type of data structure. That's one of its only major limitations, really. If you want to have a bigger array, here's what you typically do. You go and you make a whole new array, and you go and copy over all of the items from your old array over to your new array. That's not that efficient. So every time you need more room, you're doing this copy operation, and that moving over all those original items is actually pretty expensive. And so that's one of the big downsides of arrays, and one of the really major only downsides of arrays is that they have a very specific amount of slots, and each of those slots is a very specific size, and all of that is determined when the array is first created.
The second type of data structure we want to talk about is a linked list. What is that?
A linked list is another way of organizing data in a sequential form, but it has some very different trade-offs than an array has. So the big thing with an array is that we can pretty much instantly get to any of the slots once we know what index the slot is, but we're stuck with the original size. A linked list kind of has the opposite properties. It's hard to actually get to any individual item very quickly, but we can easily expand and remove items. So once we want to have one more item, we don't have to go make a whole new set of memory and copy everything over. We can just add another link in the linked list. Let's talk about that term, linked list. Okay, linked and list. Okay, list because all of the items, like an array, are going to be next to each other. However, they're linked together. They're not just contiguous. They're not next to each other in memory. They're next to each other through links. So let me talk about an abstract concept of what I'm going to call a node. Here's what a node is. A node is a little piece of memory that has some value in it, and it also has potentially a link to another node somewhere else in memory. And that's all a node is. It's just some little part of memory where there's some value. Maybe it's an integer, maybe it's a string, maybe it's a floating point number. And then there's also in that same little piece of memory a link that goes to somewhere else in memory. Maybe. And if that link does go somewhere else, it goes to somewhere else where there's another node. And in that other node, there's again a value, and then potentially another link to somewhere else in memory. So instead of having all of the things contiguous, which means that within memory they are literally next to each other, they're linked together, and so next to each other in the sense that we can travel from one to the next. But when we're actually in memory itself, where in memory that is just figured out by going across the links. It's not necessarily that it's just the exact space right next to where we started and put the first node. It could be somewhere else. It could be somewhere way further down in memory or way further up in memory, and we have to traverse that link to get to it. Now, what was so great about arrays is because arrays are contiguous, meaning they are literally next to each other, occupying all one space with all the slots right next to each other in memory. It was really fast to go from one to the next, and we could instantly go, because we could just count, to a particular index. In a linked list, because they're all over memory, we're jumping around over these links, going to one part of memory, then going to a node in a different part of memory. It's not so fast. And because they don't have indexes on each of the nodes, we can't just right away go to the next one because we don't know exactly where in memory it is. We have to actually traverse a certain number of links to get to a particular point in the linked list. So linked lists really are made up of these really simple concepts, these nodes that just have a data value and a link. And they're actually really simple to construct, which is why they're one of the first exercises people often learn in a data structures and algorithms class, or even in just a first or second level programming class. But they have this big downside that you keep jumping all over memory. But there's an upside too. The upside is that unlike with an array, when we want to add another node, all we have to do is just go make another link. We just go to the last node perhaps in the linked list and we say, hey, I'm going to create a link from you to a new node that I just made. I didn't have to go create a whole new piece of memory, like a whole new contiguous piece of memory, and copy all the old ones over. And I can even add a new link in the middle pretty easily to the linked list, or I can even add a new link all the way at the beginning before the first node that then links to that what originally was the first node. So it's really easy to add nodes. It's easier to delete nodes. It's easier to have things that expand and contract with linked lists. But it's not as fast to get to any individual node because I don't have these indexes and they're not literally right next to each other in memory.
Help us visualize a linked list. What would be an analogy for one?
A great analogy is a chain. It's literally made up of links, right? A physical chain, like a metal chain, right? And you can easily add new links. It's easy to go and take a link and put it on the end of the chain and then enclose it around that last link and you've easily expanded it. Or you can undo a link and then you've removed a link from the chain. And they're all together, but they don't have like labels on them in the same way the pillbox did. The pillbox had those labels, Monday, Friday, you could right away get to one of them. In the chain, if I want to figure out, well, which is the fifth link in the chain, I'm probably actually going to start counting from the beginning, traversing each of them and figuring out where the fifth one is. I'm not going to just be instantly able, just looking at it, oh, that's the fifth one, unless, I don't know, I'm really experienced with chains or something. I don't know. So it's a pretty good analogy. You can add and remove links pretty easily, and they're not easily labeled, so I can't just instantly go to one particular link within the chain without traversing through the rest of the links to figure out where it is.
So a software developer is going to decide based on what the project they're working on, what type of data structure is the one that they need for that particular project.
Right, and there's many more data structures than just linked lists and arrays. They might often be making a decision, though, between the two because they are really common data structures. And so if they want something with really quick lookup by an index and they're okay with having a fixed size, then they're probably going to go with arrays. And if they want something that's more flexible in terms of expanding and contracting, then they're okay with having lookups be a little slower because you have to traverse all the links, then they're probably going to want to go with a linked list. So it depends on what kind of data they're storing and what kind of operations are most going to be common, whether that's retrieval, expansion, contraction. Depending on what kind of operation is going to be the most common, they might choose one or the other based on different performance characteristics. So these were just some really basic data structures. There's actually more complex data structures that are built on top of arrays or linked lists, and there's also other fundamental data structures as well. There's so much more to learn in this area. The reason we chose these was just to give you some of the most basic overview of what these are like. If this is something that interests you, I can recommend a couple of books. I'll recommend Introduction to Algorithms. I'll recommend Algorithms by Sedgwick and Wayne. And I'll also just recommend some of the basic Khan Academy courses on data structures and algorithms, which are pretty good as well. They all have a lot more detail about this. They're all geared towards people who are going to be computer programmers or studying computer science. So if that's not you, maybe this is as much as you needed to just have a concept of what this is. In a future episode, we're going to talk about algorithms, and you might wonder, why are the books called like Algorithms, Introduction to Algorithms, if they actually teach you a lot about data structures. Data structures are used and considered fundamental building blocks of most algorithms. So you need to know data structures to be able to do a lot of algorithms. And so we will talk more about algorithms, which is a buzzword that I'm sure everyone's familiar with, even if they're not familiar with data structures, in a future episode. Thanks for listening to us this week. Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
Thanks for listening. Have a great week.
Bye.